Thank you, Adam. I am also quite impressed to see such a wonderful turnout. Thank you all for coming. Tonight, I will be talking about clustering customers to predict lifetime value. So before we get started, let me share a little bit about myself. So I am currently a senior data scientist at Retina. My background is mostly in math and optimization and machine learning. So everything related to models and why we choose them the way we do, how we evaluate them, these are all things I love to think about, and the mathematical underpinnings that come along with that. So to test these different ideas, these different models, I often find myself using R and Python, usually more Python, but more and more R. And I'm new to the LA community. I've only been here for about 9 months, and I've been trying to meet new people through these meetups, and then so please, I encourage you to come by and say hello, and I'd love to meet new people and learn more about what's great about living in LA. So for this talk, we're going to be talking about a lot of clustering. Clustering is one of my favorite topics, and then mapping that back to customers and what can we do to understand customers by clustering them. So we'll start off with a quick little story about what the business value could be. We'll briefly jump into some of the model and the math and the data structure behind what we do and what those requirements would look like. But then we'll wrap up with a little example in R that actually leverages the package from H2O.ai that will make it very, very easy for anyone in the audience to be able to take these concepts and apply them to their own work. So first, let's set the stage. Imagine that you sell animal cookies through your website. And you have some customers that come to your website. They might buy some packs. They might subscribe online, and you're able to track these visits as sessions data. So what's interesting here is that you can start to see what type of people are visiting your website, and you can gather more information about those who do purchase from your site. But even if they don't, you learn something about those types of customers. So you might want to ask yourself, like, how if I'm going to create a campaign to try and retarget or acquire some of these visitors to my site, whom should I target and why? So what we're going to talk about now is there a way that we can build this metric? This metric is customer lifetime value, and use that to estimate how valuable customers are. But the trick is here that for customer lifetime value, you normally need some sort of information about their purchase history. You normally need things like how often are they purchasing, how much do they spend, how likely are they to continue to come back and purchase more. So is there a way that we can get a sense for how valuable these customers are, even if they haven't purchased anything at all yet? So that's where clustering comes in. So the idea here is that once you have this way of gauging how valuable some of your customers are, like maybe they've been repeat customers and they're highly valuable, maybe they live in a particular state or have a particular device type that they use a lot when they're browsing your site, and these are valuable, and you ask yourselves, how do I find customers who are similar? There are a few different ways to cluster. In general, supervised learning, you would build a decision tree that would tell you if I take the logical break here, then I can predict. I can basically train a model that will predict the value if I know for some customers in my train set how valuable they'll be. You can do the same thing with k-nearest neighbors, but most of the time you might not have labels. So I guess take a step back here. The difference between the supervised learning and the unsupervised learning from a clustering point of view is whether you want to build a predictive clustering scheme where you use the features to decide whether those customers are valuable or whether there's a label that you can predict. Or in the unsupervised learning case, you're just trying to be descriptive about who your customers are, how they're similar, and what makes them similar and to what degree they're similar. But like all machine learning models, there are plenty of ways that this can break. There are plenty of ways that the models that you use out of the box just don't work on your data. So to really see where this could fail, let's take a look at some data, some sample data from our website. We might be able to track device type, acquisition channel, things about our customers like flavor, favorite shape. These are things that we might ask from some of our customers. And once we have those questions that are filled out, we have this complete data set. Now, the CLV, this is customer lifetime value. This is something that we can compute. Or we could even substitute that out for total spend. Maybe we only want to look at how much our customer's spending. But this usually isn't the kind of data that we start with. Normally we'll have customers A through C where we happen to have all this data, and that last customer, we don't know how much they'll spend. We don't know whether they'll subscribe with us. Maybe they're just so young in their customer journey that we don't know what kind of customer they'll be. But we know these things like the device type, the channel at which they are acquired. We know their favorite shape through this quiz. So we might want to use that information to make predictions about what kind of spender they'll be. Now, there are other things that can happen too. Let me try this. Hello, does this work? Oh, that one sounds a little bit better. Great, so going back to this quiz question, right? We give a quiz to all of our visitors. Some of them might not answer, right? Customer B doesn't answer.
Hey, Corinne, you want to just go for the without the mic so it happens?
Sure, let me try that. Can you guys hear me?
Yeah.
All right, I think this will be a little more natural. I'll turn that off. Okay, great. So back to our data. We have some customers who respond and give us information. We want to leverage that information. There are other customers who don't, but we don't want to ignore what we do know about them. We don't want to ignore the fact that we have these new types of customers coming in through Google or coming in on a mobile device. So what we really want to do is we want to cluster in a way where we don't have to throw out these data points, and we want to be able to still predict these things we care about. Customer value, spend, whether or not they will be subscribers or return customers. So this is where this new model comes in, and we're going to call it generalized low-rank models. And the reason we're calling it generalized is that it takes these concepts that we see from other clustering models. A support vector machine, k-means clustering, principal components analysis. There's one concept that these all have in common. And that concept is there's a way to group your customers in a way that will best represent your original data. So now what we're going to do is we're going to try and apply this model to our animal cookie customer data set so that we can make those predictions about who will be the high-value customers, but we'll also have descriptions about who our different personas are so that we can build, say, targeted marketing campaigns or other, we can specialize other approaches for those types of personas. So before I move on to the next slide, this is a topic that we're only going to scratch the surface on today. Like I said, my background's in more math and optimization, and this is a purely optimization class of models. So I'm throwing this out there, the GLRM term, so that if you want to use this tool later on and say R using H2O, that'll sort of be the keyword to look at. But there's a lot more to talk about and dive into here that we're just not going to touch on today. What I do want to point out is sort of how all those different clustering techniques do relate to each other. And I promise this is the only slide that looks like this. But what you can do is you start with your data. That's this A on the left. And you want to break it up. You want to find this low-rank approximation represented by X and Y. So X here are going to be, for each of my customers, each of the M customers, each row is a customer, which of those K clusters do they fall into? Now, the Y, the fat matrix, is now going to show for each of your K customers what type of features do they have. So that's why there's K rows and N columns. So if you were to take the top row in Y, that would be one archetype or one persona that describes an independent subset of your customers. Now, the key thing here is this little tilde that says approximate. So you want to find this clustering scheme on the right that best approximates your data on the left. And if you were to walk in and start thinking about like how does this map to PCA, well, I can tell you the way it maps to PCA is the approximation metric here is you want to minimize your total sum of squared loss, the total sum of the squared values in the error of your entries. So if you find a way to choose X and Y that minimizes that, that's PCA. If you come in and you say, well, you know what, I only want my customers to be assigned to one cluster, then that gives you k-means clustering. But when you start having these weird data types, like you might have someone who subscribes or doesn't, you might have somebody who is using a mobile device or a desktop or coming in through a different source, and how do you even measure how how good those approximations are. If I guess that one customer in this cluster is using mobile and then in reality they use desktop, like how do I even evaluate how good my clustering is? So that's where that approximation, that tilde, comes in. You get to choose what the similarity looks like. And you can use that to scale up certain things that are important to fit. For example, if I really want to build a clustering scheme that it's fairly descriptive of my customers, but most importantly, it will help me predict certain things that I don't know, then I will say put more weight, put more loss for getting that estimation wrong on that one thing I care about. And everything else I care about it, but I care about it less. So you can go in and you can start tuning this. And that's really where the power of this generalized approach comes in. So that's enough math. Let's go ahead and show you, jump in, and walk through an example of how we can actually use this in just a few lines of R code. So what this is, H2O to AI is an R package that is through an open source project called H2O to AI that is intended to make available a lot of machine learning tools and make them as easy as possible to implement. So there's a lot of details here that I don't really want to necessarily touch on now, but we do intend to make this slide deck accessible. So this is something that maybe we can reference further on. But the important thing is, we're choosing this loss. We're careful about how we're going to measure how well our clusters actually, how well our clusters and those estimations made by clusters approximate our original data. So what I'm doing here in this little example is I'm saying use this sum of squared loss, only let a customer be assigned to one cluster rather than being, weighted across several. The alternative is you might say you could maybe count one customer as being 50% over here, 20% over here, 10% here. But no, we're going to say they only belong to one cluster. And we are going to force our clusters to be non-negative, which just means we want to be able to understand, what they mean. If we're talking about counts or dollars, we don't want that to be negative. We don't want this to be difficult to interpret. And then here I'm choosing the number of clusters. So in this next step, what I'm doing is I'm actually loading in real data from a client of ours. It's been anonymized, so you can't actually, it's been changed and the features have been modified under a transform, so you can't actually reverse engineer who it is. But this is sort of the output of what we get. Our goal is to predict revenue by customers, and about 40% of the customers have no revenue available at all, so they're just treated as missing values, not available in our matrix here. The output of this generalized low-rank model will give us which customers are assigned to each of these different archetypes, and then use that to guess what the revenue is. So if you track for each customer, let's look at the first and the fifth. They're both assigned to the seventh cluster here. So they both have the same predicted revenue of $107.75. So what we're doing here is we're finding this clustering. We're using that to fill in those missing values by looking at what the archetype or what the cluster center is for that group that they're assigned to. So we're grouping customers by others, into similar groups, and then we're looking at the average aggregate over that group to get a sense for what we could have. So wrapping this up, we want to use this generalized model to create these different personas, and the key thing here is that we're being both descriptive and predictive in our clustering. We're not going to rely on just supervised or unsupervised. We're going to actually find a nice blend of the two and give ourselves the freedom to decide how much of each one is important to us. We're also going to be, adding value by finding a way to make predictions about customer value by looking at what those personas or what those archetypes actually are for the within the clusters that people are assigned to. Now, the real value here is that we don't have to throw out any data, and if there are some features that we have very little information about, say like answers to a quiz question, maybe 5% of your customers could fill it out, you can still leverage that. You can still guess, you can still cluster and use that to project onto the entire corpus what you expect that to look like for other customers. So wrapping up, we have a lot of references in this talk, and this is a really high level, supposed to graze the surface and kind of get people excited about clustering. But we are always thinking about new ways to apply this to customers in order to reach more insights. So if there's any other questions that you have now or later, feel free to reach out to us. Yeah, thank you. yeah, are there any questions? Go ahead.
So you started with a guess as to how many clusters. What would the steps be to get to the rate?
Yes. So, you know, a very typical way to guess the number of clusters is to start with a small number, maybe 3 or 4, fit the model, look at the total approximation error across all of your data, and then continue to add more clusters and plot that. And the error will go down the more clusters you have, but there'll be an elbow somewhere in the curve. So that's a very common way to approach it. Because we have so many design parameters in this modeling scheme, you can also imagine that if you choose a different set of weights or loss functions, you can get different elbows. So it is going to be a function of what you're looking for. In fact, I'd also argue that going into this, it depends on your business context. If your goal is to cluster customers so that your marketing team can write copy for them, then you don't want to have more than 10, right? Because that would just make their job more miserable. If you actually want to minimize your error for longer term predictions or something that is more important to get correct, then you might want to let yourself up at a 20 or 30. And of course, it will depend on how many features you have in the first place. But looking at that elbow is also a very good way to do a sanity check. Yeah. Yeah. Mm-hmm.
Driverless AI, did that come into play at all here? The show us a number of offerings. Which ones were you using?
So I heard driverless AI.
Yeah.
And what was your question?
Were there other H2O products that kind of went into this?
Okay, so the question is, we're using H2O to AI to achieve this, to build a model on our large data set. And H2O to AI is a way to sort of build scalable machine learning models. And we chose this model, the JLRM, because it's something that I worked on in the past. And in fact, a colleague of mine is the one who actually built out the H2O to AI package. So between the experience I had working on some of the math side and her experience building out the software, that was sort of why we chose this. But there are other, we mentioned that principal components analysis is a special case, so there are simpler approaches that don't require the heavy generalized machinery. But it is, we've only really looked at this one model because of my own background with this before. Yeah.
That is the H2O open source package, not the H2O product.
Oh, yes. It's an open source package.
H2O does other things, including driverless AI.
Ah, okay. Sorry, I misunderstood the question.
So yeah, in your example, you used in that case site visitation and then potentially past records of purchase history in that case. At what point do you then, perhaps for clients, enrich some of the first-party data to essentially make better predictions? Or in that case, is that enough to come up with good predictions?
Yeah. So to make sure I get your question right, you're asking, we're using a lot of customer data, first-party customer data, and at what point do we add on new columns that we will use to make better predictions?
Yeah, for instance, in one of the examples, we know in that case where people came from, what browser type, desktop size, if that's important, as well as their purchase history. There's also the ability to, in that case, acquire more information about that individual, be it in that case, household, kids in household, lifestyle, personality traits, and so on. To what degree has that been done? Or in that case, does that actually need to be done to further improve the model?
Yeah, so I can speak to what we would have available and what we can do with what's available to us. The question of is that enough data? That's a different question. But at Retina, we work with customer data that they provide us, and so we might make recommendations that this is enough to do these things and make these inferences, or it's not enough. But we really work with what we have available to us, and we don't make a concerted effort to combine outside data with what we have, but we do also append the data. We augment the data that our customers give us with these, say, estimates of lifetime value. We also add new columns like probability of churning, or how likely they are to come back in, say, the next year. And so we can add on these new statistics, which we can then use to further cluster should we want to. Yeah. Does that answer your question?
Yeah.
Okay, great. So we have time for one more question.
So
you're talking about adding the weights to the different losses, so to have one label with more weight for loss for that one more. Are those derived from business decisions, or is that something that you tune?
It's a little bit of both. So the real answer is it's tuning, but to know where to start, that's where I would ask business experts. And where would you start? What direction do you think it should go? I might ask, for example, how much more important is this thing than the other, and then use that as a starting point, and then move around from there. And it's a very, all machine learning models are very difficult to wield because there's so many hyperparameters, so many things that can go wrong, so many things that make it difficult just to use these programs. So it's really like communicating with experts, but also searching. Yeah. Yep.
This one question is related.
Okay.
On the processor side, like with all the issues that come up with GPUs, are you able to affect that?
So your question was.
So a lot of times we do analysis on the, let's say, the graph, but part of my team has been working a lot on the eGPU to figure out what it's doing in the background. We're learning a lot, especially in CUDA, some of the flaws. Computation. Device architecture is the software that runs most of the machine learning that run on a GPU. We're just finding that there's a lot of pitfalls if you don't use it properly. You don't change your equations, your results. Have you found that, or are you guys looking into the hardware effects on the graphs?
So it sounds like, I believe your question is related to an implementation of the model using GPUs. Sometimes if you fit a model using the GPUs, you might get a different answer from like one start than a different start, right? Or there might be other difficult things that break.
Or if you break down there, you realize that it's biasing in a way it shouldn't.
Yeah, so that sounds like a question that's very much related to neural networks. And this is actually a little bit different than neural networks. It's mostly unsupervised. It's supervised in the sense that you want to be able to approximate things well, but we're actually not training any sort of neural architecture.
But a cluster itself is going to use a certain amount of memory, and that's what we're finding the problem. Whereas if you don't use either the full amount of memory or jump up or jump down, it actually just throws away part of your data.
Yeah, so unfortunately I can't speak too much about like memory issues related to some of those larger model or the fitting a lot of data to some of the like more complicated models. What I can say is for most of these machine learning models, they might depend on how you make an initial guess, right? For neural networks, for example, you can seed them one way and fit the neural network, and then if you come back a year later with the exact same data, you might still train a different model with different layers and different biases that are learned. So that is a nuanced aspect of the model itself, and I'm happy to talk more about that offline. But there are some mathematical reasons that you can say like this will or will not be the same answer, and with what certainty. So, yeah. Okay, that's it.